Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, exactly 1 week ago. It introduces a new framework called InteractAvatar, which improves the quality of generated hands by roughly 180% and object interactions by over 100% compared to strong baselines. The paper is titled, Making Avatars Interact, Towards Text-Driven Human-Object Interaction for Controllable Talking Avatars. And, as we'll see later, the results are really impressive, promising a major shift from simple talking heads to fully interactive digital humans. So, Figure 1 illustrates the core capabilities of the InteractAvatar framework. The large section on the left highlights the main innovation, grounded human-object interaction. Here, the model generates complex actions, like a character removing eyeglasses or picking up an apple, strictly following the reference image. Then, the top right panel demonstrates pure human action generation, such as hand gestures, while the bottom right shows the model can still produce synchronized talking heads. Alright, Figure 2 details the system architecture. It begins on the left with feature extraction, where inputs like images and text are encoded. The core innovation is in the middle, a dual-stream design. The bottom path is the perception and interaction module, which acts as a planner to generate motion trajectories. The top path is the audio interaction-aware generation module, which functions as the renderer. Crucially, the motion-to-video aligner connects them, injecting motion structure into the video generation to ensure alignment. Finally, the right side outlines the strategy, moving from separate pre-training to joint fine-tuning. Well, having seen the architecture, Table 2 now validates the training strategy for the perception and interaction module. This table breaks down an ablation study where components like rope embeddings and detection tasks are added incrementally in the left columns. The metrics on the right track the resulting performance, specifically focusing on hand quality and object quality. The data reveals a clear trend. The bottom row, which enables the full detection and continuation curriculum, achieves the highest scores across the board. This confirms that forcing the model to explicitly learn object trajectories during training directly translates to more realistic interactions. So while the previous table confirmed the training strategy, Figure 3 demonstrates the visual impact. The top row sets the stage with text prompts like picking up an apple or raising a camera. Beneath that, the middle rows show baseline models like WAN, S2V, and Humo, often failing. They frequently ignore the object or distort the hands. Finally, the bottom row reveals the results from InteractAvatar. As the green boxes highlight, this method successfully executes the interactions while preserving the original character and environment. Alright, Figure 3 showed the visual improvements, and now Table 1 quantifies them on the grounded interbenchmark. The table organizes results by input signal, separating audio-driven, pose-driven, and text-driven tasks. The most significant gains appear in the human-object interaction columns, particularly for hand quality and object quality. In the audio-driven section, for instance, the hand quality score reaches 0.93, effectively tripling the performance of the WAN S2V baseline. Well, Figure 4 visualizes the critical role of the perception and interaction module. The image compares different configurations for tasks, like shooting a basketball on the left, or picking up a phone on the right. In the middle row, which removes the perception module, the model hallucinates the motion without moving the object. Notice on the right how the man mimes picking up the phone, but the device stays frozen on the bed. In contrast, the bottom row uses the full framework, allowing the avatar to actually grasp and lift the object realistically. So, while the previous figures showed the qualitative difference, Table 3 provides the quantitative ablation study. The top section focuses on the architecture, testing different ways to integrate the perception and interaction module. We see clearly that removing the module, in the first row, drops the hand quality score to 0.711, whereas the proposed method reaches 0.925. Then, the bottom section evaluates the training schedule. The results in the final column highlight that the full multi-stage strategy is necessary to maintain high audio synchronization, scoring 5.43. Wrapping up, two takeaways stand out. InteractAvatar successfully bridges the gap between simple talking heads and fully interactive digital humans. By decoupling motion planning from video rendering, it achieves a massive leap in hand and object interaction quality without sacrificing visual fidelity. This points toward a future where avatars can genuinely inhabit and manipulate their environments. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.